Hello, in section 10.2 we're looking at mole mass and mole volume relationships. Specifically, we're trying to convert between moles to mass or moles to volume and vice versa. Let's first start with a review problem that should seem pretty basic to us. This is a review of Algebra 1 and it's called dimensional analysis. We're going to take a look at converting 3,200 meters to miles. To do this, we begin by recording what we know and what we don't know. We know that we have 3,200 meters and we don't know the number of miles. Our conversion is we start with what we know, 3,200 meters, and we're going to put this in fraction form, so over 1, times a conversion factor. When we're doing dimensional analysis, we're trying to cancel out this original label, meters. And to do so, we're going to put this on the opposite side of the fraction in our conversion factor. So for every, for every 1 mile is what we're trying to convert to, there are 1,600 meters. And we see here that our conversion, our labels actually cancel out here. We've canceled out the meters. And the only label left in our answer is miles. So when we do the math, we have 3,200 is the only value left in the numerator, and the label left in the numerator is miles, divided by 1,600. Simply on the calculator we divide this and we're going to get 2 miles as our final answer. Again, this is called dimensional analysis. It's converting units. We went from meters to miles. So we introduced what we know. We used a conversion factor, this portion right here. We used multiply by the conversion factor. We simplified the numerator and denominator. We canceled out our labels and we're left with 2 miles as our final answer. This same strategy is useful when we're comparing moles to mass and moles to volume and so forth. So, let's do a simple problem with converting moles to mass. We're going to calculate the mass in grams of 2.5 moles of iron 2 hydroxide. Well, we know that what we do know we have is 2.5 moles, and that's the abbreviation for mole, of iron 2 hydroxide. So, if you need to recall how to go from the name to the molecular formula, you should check back to chapter 9. We know it's iron 2 hydroxide, so this is a 2+ species, and then hydroxide ions are a 1-, so by crisscrossing those charges we get FeOH2. Something else that we know that 1 mole of iron hydroxide is equal to 89.8 grams. And again, this is a review of section 10.1. We would look up the molar mass of iron, and we have 2 oxygens and 2 hydrogens. We combine the molar masses of all of those to figure out what 1 mole of those molecules' mass is worth. Ultimately, as we're still in the analysis section, we're trying to solve for the number of grams. That's our unknown. Alright, to calculate, we're going to use the conversion that we're going to convert the moles to mass. And so, much like up here in the previous example, we start with what we know, 2.5 moles and I like to put that over the value of 1, make it a fraction, times the molar mass hang on 1 second here, let me clean that up. Alright, we are trying to go to cancel the moles out. So I want to make sure that I have the conversion factor. I want to make sure that moles is in the denominator in this conversion term. And so when I go back through and cancel out my labels, I have mole canceled out here and here. I actually could cancel out the FeOH2 as well, and I'm left with these two labels, grams and FeOH2. And again, I was trying to solve for grams, so I can see that I've done the correct conversion factor. I'm going to continue with the math here. I'm basically going to have, across the numerator, you're going to have 2.5 times 89.8 fix that there, 89.8 grams. And when we solve that, we should come up with 225 grams FeOH2. And that's my final answer. Alright, evaluate. What we're trying to do is, does this make sense? I have about 2.5 moles, and 1 mole weighs about 89.8, let's say 90 grams. So 2.5 times 90, am I expecting a number greater than 200? Yes, that's about right. So, seems like I've got a pretty legitimate answer here. Let's move on down. Let's try another one. Let's go backwards. We're going to go mass to moles here. And so we're going to list what we know. We know that we have the mass equals 75.0 grams of N2O3. It's a molecular compound. I know that because it has the prefixes, the numeric prefixes, 2 nitrogens, 3 oxygens. That's a bit of a review. And I'm trying to solve for, I don't know how many moles, so moles is in a question mark here. I'm going to convert mass to moles is my conversion, and I list what I know. I have 75.0 grams N2O3, and I'm going to multiply that by a conversion factor. I always try to get rid of the grams, so the next one I'm going to put grams down here. I look up the molar mass of N2O3 and I find that it's 76 grams per mole. So there's 76 grams in 1 mole of N2O3. And I can figure that out again by reviewing my periodic table. Nitrogen has a mass of 1 mole of nitrogen has 14 grams in a mole, and I've got 2 of those moles, so that's going to be 28, and then oxygen 16 times 3, so add all those values together, that gets me up to 76 grams per mole. Alright, back to it here. So I'm going to do some label cancellation. I've got grams here and here. I've got N2O3 here and here. I'm left with these 2 labels. That's my answer over here. And they're in the numerators. Let me put that back in black. I do the math. 75 grams is left in the numerator. And 76 is in the denominator. When I take 75 and divide by 76, I am left with 0.987 moles of N2O3. Evaluate. Does this answer make sense? I've got 75 grams. It's being divided by 76 grams per mole. Roughly, that should be something of a value of less than 1. So that seems pretty legit. Alright, back to Avogadro. Avogadro is working with these mole relationships, mole to mass, and also he's going to do some work with mole to volume. And in doing so, he finds that that volumes of a gas can change due to atmospheric pressure or temperature, and so we need a relative way of communicating these ideas. So he comes up with what we term standard temperature and pressure, and that standard temperature is 0 degrees Celsius at 1 atmosphere. 1 atmosphere is going to be at sea level. So pick a cold place, maybe the shorelines of British Columbia or Nova Scotia. It's a cold day, so it's 0 degrees Celsius, or it's just around freezing, and when you're at sea level, you're pretty close to being at 1 atmosphere of pressure. Note that there are different weather patterns that can change the atmospheric pressure, and so scientists have to take into account when they're working with meticulous data what's going on in the current weather, and also the altitude. Here in Vail, we have thinner air due to our altitude, so we have less atmospheric pressure, and so we'll get some numbers kind of skewed by that. We have to employ, if we're trying to find exact values, there are like some conversion charts we could connect with to convert it to standard temperature and pressure. But that's neither here nor there right now. That's just kind of an FYI. Let's go back to Avogadro. As he's working with the volume of gases, gases are difficult. If you just take a balloon of oxygen and put it on like a balance, it's not going to read very much. If you put a balloon of helium on a balance, the mass is going to seem like it floats. How are you going to get the mass of it? And so the idea here is, if you jump into a swimming pool, we know that we have mass. Yet when we're in the pool, we're buoyant. We're floating in that liquid due to our density. We have relatively a similar density as all the water there. And so we get this kind of weightless feeling. And the same occurs with volumes of gas. It's difficult to get the mass of them when they're, in essence, floating in a pool of other gases around that balance. What Avogadro found an easier way, he compared the volume of a mole of argon and the volume of a mole of oxygen and nitrogen gas, and found that they take up the same exact amount of space. All three of them roughly are around 22.4 liters of space. All right. If we look back up, this shows us what 22.4 liters at standard temperature and pressure is. All right. It's about the size of a medium U-Haul moving box. You could fit a couple different backyard sports balls in there, such as a soccer ball and such. You could put a couple of them in that amount of space. So we know that 1 mole of argon from the periodic table's atomic mass is 40 grams. 1 mole is 40 grams, and it will take up 22.4 liters of space. Meanwhile, oxygen is 32 grams, and it'll take up, again, the same amount of space. So they have relative different masses per molar volume, which is important, as we'll see later when we look at some things like density. So equal volume of gases at the same temperature and pressure contain an equal number of particles. That's pretty neat. That's a unifying principle that we can use to make some future conversions. So under standard temperature and pressure, what does 1.25 moles of helium occupy? We're going to analyze this first by listing what we know. So we know that we have 1.25 moles of helium gas, and we're trying to find the volume of helium. So liters of helium is a question mark. We're going to calculate. So we're going to do a conversion here. We're converting the moles to the volume. And let's plug in some numbers here. We have 1.25 moles of helium is what we're starting with. And much like last time when we're doing dimensional analysis, we're going to try to cancel out this initial unit. So we're going to be putting moles on the bottom of helium. In 1 mole, there's how many liters? Well, from before, we recognize that 1 mole of any gas will have a volume of 22.4 liters. That's our conversion factor. Now we do some canceling out of the labels. Mole, they cancel. Helium, they cancel. We're left with liters in helium in our final answer. And so when we multiply here, we would literally do 1.25 times 22.4 on our calculator. That answer is 28.0 liters of helium. And that's a final answer. Does that make sense? Let's evaluate this. We have a little bit more than a mole. And so we've got about 1 1/4 moles here, and we would expect that should be a little bit greater than 22.4 liters, and that seems to make sense here. So let's move on down here. Let's see one related to density. A gas has a density of 0.902 grams per liter. What is the molar mass of this gas? Let's see here. Let's start with a real basic relationship. Recall. Density equals, what's the formula for density? Density equals broken heart. All right. So on top now we see that we have the M, and on the bottom we have a V, the broken heart. So density equals mass divided by volume. We are given, we can also convert this formula. Let's do that briefly. So if we, in this problem, we're trying to find the molar mass. So in grams, we don't know. We're trying to find grams. We're trying to find mass. To isolate for mass, we would move the volume, over to the other side. So we'd multiply by V on both sides. So we could manipulate the formula so that mass equals density times volume using some basic algebraic skills. And let's see here. We know, so this is a useful formula, and we know that density from the given information is 0.902 grams per every liter. And we also know that we know a little bit about the volume. If we were working with 1 mole of that substance, we're going to have 22.4 liters. In this problem, we have to make a bit of an assumption. Let's just use 1 whole mole in our example to find the molar mass. That makes sense, right? We want to find the molar mass. Let's take a whole large amount, 1 mole, 22.4 liters, and plug it in. So we're going to use that formula, mass equals density times volume. We know that the density is 0.902 grams per 1 liter of, we don't even know what the gas is, so we don't have to have any more labels there, times a conversion here. We're going to, not a conversion, we're going to multiply by a volume here. Here's our volume. We have 22.4 liters, and that's the volume of 1 mole. And so the mass equals, we take 0.902 times 22.4, and that gives us, on our calculator, we read out 20.2 grams per mole. So there we have it. Let's take a look back and evaluate this. Molar mass. The label for molar mass is we have grams per mole. And if we compare here, did that come out? Yep, we have grams in the numerator and moles in the denominator. All right. This is a nice cheat sheet that we find near the end of section 10.2, and I just wanted to briefly talk about how it works. We've got a couple of different locations we can start from. We can start from the volume of a substance, the representative particles of a substance, or the mass, or we may even know how many moles that we have. So 4 locations. Let's say that I tell you that we know the number of moles and we want to get to volume is our unknown. So here's our known, and here's our unknown. Alright, we would take our known, such as the amount of mass, so the number of moles, so the number of moles, and we're going to multiply it by a conversion factor. So we're at moles, and we're trying to figure out the volume, so we're going to move in this way. This is our conversion factor. 22.4 liters over 1 mole. So we take the number of moles, and we multiply it, and that'll provide us the answer to our unknown. If we worked it from volume in reverse to mole, we could take the amount of liters, so the number of liters of a substance, and multiply it by this conversion factor. Here we're going the opposite way. So my conversion factor is 1 mole over 22.4 liters. And I multiply it out, or actually, I'm going to be dividing here, and it's going to give me my unknown. And so this can work in a variety of ways. If we want to go from moles to the number of particles, we would multiply by this value here. And vice versa, if we knew the number of particles, we're going to use this conversion, and so forth. If we're going from moles to mass, or from mass to moles, again, nice little cheat sheet. I would, in fact, though, have to know the molar mass. And where do I find that? Oh, yes, by looking back to the periodic table at the atomic masses. Great. That wraps it up for section 10.2, converting known quantities to unknown quantities, so making conversions. Thank you.